Let me welcome Divesh Aggarwal.
Yeah. So, thanks a lot for inviting me. I'll be talking about this recent work, new public ecosystem by Mersenne numbers, and as was just said, I mean this has nothing to do with elliptic curves, and it has not so much to do with lattices as well. But like, okay, the best attacks are using lattices. It's a fairly simple system, and I hope I can explain it like completely in this 40 minutes. So, okay, so okay. So this is joint work with Anton Yu, Anupam Prakash, and Miklo Sangha, and this was presented at Crypto this year. So let me go straight in. So public key crypto systems were introduced by Diffie and Hellman back in 1976, and there have been plenty of candidates over the years. Maybe not too many, but still like I've seen many candidates. And then in the more recent years, people have started building more advanced primitives like fully or encryption or in this obfuscation. So, and in this work, we kind of go back to integrating a new public system. We propose a new public key scheme, which we think is like simpler than almost anything that we've seen earlier. And we also believe that it is secure against quantum attacks. At least we don't know of any quantum attack scheme. Okay, so this crypto system, it can be classified in this, as we call it, the class of so-called ring and noise family of systems. Basically, I mean, what I mean by ring and noise is that the basic operation is happening in some certain ring, and then just to make the task of recovering the secret key from the public key harder, we add some noise in some way. And like you can see that basically NTRU or code-based crypto systems or learning with error-based crypto systems all kind of fall in this category. So, but we'll be working with a different ring. The ring will be the ring of integers modulo a prime, and the prime key would be a Mersenne prime. So, and the noise would also be different. So, here we'll be talking about the noise would be Hamming-based modulo the prime. And like for all of these ring and noise kind of family, the noise is typically very unrelated from the ring. I mean, and so is the case here. So you see that like basically we're not talking about the small element in the ring, but we're talking about a small Hamming. Okay, so what are Mersenne primes? These are primes of the form 2 to the n minus 1, where n is also a prime. And this is named after a French mathematician called Mersenne, who studied these kind of numbers in the early 17th there are some 50 of them that are known currently, and like it's believed that there are infinitely many of those things. And so we'll be building our cryptosystem on this scheme, and as I said, the main advantage of a cryptosystem would be simplicity. So the ring is the ring of integers modulo the Mersenne prime, the prime of the form 2 to the n minus 1. So our P will be this 2 to the n minus 1, so I'll be keeping this number n fixed throughout the term. And then the representation of x, I denote it as RCX. It's the representation of x in numbers from 0 to p minus 1. Right? And the Hamming weight of x is the number of ones in the binary representation of x modulo. So there's a unique way to write a number in form 0 to p minus 1, and then you can just write the binary representation and count the number of ones there. Okay, so why do we work with this thing? Let's look at some properties of arithmetic modulo Mersenne prime, which are very attractive and which lead us to basically working with this. So the first property that I mentioned here is that when you take the Hamming weight of the sum of two strings, that is upper bounded by the sum of the Hamming weight of them. It's not too hard to see. So let's try to kind of see this. Let us add, basically let's say that Hamming weight of y is some number h, and let us add a Hamming weight one string, one at a time basically. So we'll have to do this operation h times if the Hamming weight of y is h. So this is an operation for adding a 1-bit string. So notice that when you add a 1-bit string, what you do is basically you look at the first 0 preceding you look at the position corresponding to this one, then you look at the first 0 that is appearing, and then this 0, 1, 1, 1 string changes to 1, 0, 0, 0. So you notice that the Hamming weight basically can increase only by at most 1, and it is generally the number of Hamming weight changes by 1 minus the number of ones that you have here. So it will basically increase by at most 1, but it will typically go down, right? And so when we add a string of Hamming weight h, we would increase the Hamming weight by at most h. And just as I repeat it again, like you would typically expect it to not go up. And the second property that I mentioned here is that when you multiply a power of 2, the Hamming weight of x remains the same. This is because this is quite easy to see, because whenever you multiply a number by 2 to the I, the corresponding string just shifts by I positions. So if the Hamming weight does not change, right? Because we are doing everything modulo 2 to the n minus. So whenever you cycle, it's cycling by I position. And the third property, which is that Hamming weight of product is upper bounded to the product is the Hamming weight. This just follows by induction on property 1. Because we have the sum is upper bounded by the Hamming weight of sum, so you can just do this particular operation. You can write this Hamming weight of x times Hamming weight of y. So you can write this as a sum of, so just like basically multiplication distributes over it. And the Hamming weight of negative of x is simply, you can think of negative of x as just p minus x, which is the same as an all one string minus x. So you just flip the string, and so the Hamming weight is exactly n minus the Hamming weight. Sorry. Okay. So these are the properties that are going to be very useful for describing a cryptosystem. So let me go with the first version of the cryptosystem that encrypts 1 bit at a time. Okay. So we're talking about numbers of the form 2 to the n minus 1, and we have some parameter h, which is going to be bound on the Hamming weight of strings f and g. So we have so we take f and g to be numbers modulo p with few ones in their binary. So it is a integer string with a small Hamming weight. And then we take capital H to be the ratio of these f and g modulo p. So, sorry, but what I want to say is the assumption is given H, it is hard to obtain F and G. So these are difficult to obtain, and that's the hard problem that you would be facing at the system. So that given H, it is difficult to get any information about that. Notice that even though F and G have small Hamming weight, this you would, when you take the ratio, you would expect this to look very nice. I showed an example. Okay, so here's how we encrypt. So the H, the string which is F divided by G modulo P, this forms the public key of the crypto system, and the secret key is just the string G, small Hamming P. And the way we encrypt is we pick A and B to be two numbers with the small Hamming weight, and then let the encoding of 0 be A times H plus B, and the encoding of 1 is negative of A times H plus B. And the way we decrypt is just multiply the ciphertext C by G, and notice that in the case when we have the encryption of 0, when you multiply by G, you will get, so the H is simply F divided by G. When you multiply by G, you will get A times F plus B times G. And when you have an encryption of 1, you will get minus of A times F plus B times G. And what you do is then you compute the Hamming weight of G times C, and the output, we decrypt to 0 if G times C has small Hamming weight, and we decrypt to 1 if G times C has large. So this is a simple toy example. So think of P as this 2 to the 31 minus 1. So this is written in decimal notation, and this is the hexadecimal representation of P. Then let's say H is just the ratio of two small Hamming weight strings, F divided by G. So notice that even though F and G have small Hamming weight, when you take their ratio, this string looks very nice. This would be, this would be true for any. Try this string, when you take the ratio, will look great. So when we encrypt, what we do is we pick again A and B to be two small Hamming weight strings, and then we encrypt 0 as A times H plus B, so this again gives us a very nice string. But when you take the product of the C with G, you would get a somewhat low Hamming weight string. So this looks like low Hamming weight string, and we can compute the Hamming weight of G. This is 8, which is less than half of the maximum Hamming weight. So we decrypt to 0. So what is the rationale for the correctness? Notice that when we did G times G times AH plus B, this was what we were doing for decrypting, we get AF plus BG. So when we encrypted 0, we got A times F plus B times G after running the decryption operation. And the Hamming weight of this is upper bounded by Hamming weight of A times Hamming weight of F, the Hamming weight of B times Hamming weight of G, which is at most 2x squared. So as long as we pick n to be bigger than 4x squared, the Hamming weight of this term would be upper bounded by half of the Hamming weight of half the maximum. And when we did an encryption of 1, we would get just the negative of that. So the Hamming weight of this would be at least n minus n minus this part. So it will be at least n divided by. As long as n is bigger than 4x squared, we have the Hamming weight of the encryption of 0. So sorry, with G times the encryption of 0 is small, and the Hamming weight of G times the encryption of 1 is large. And this we can use to decrypt. So let me go now to when we encrypt more than one bit at a time. So how do we do it? So in the previous case, what we had was we had H as our public key, which was F divided by G, and F and G had small Hamming. So we can write this. I mean, like we can also rewrite this equation in this form. So F times 1 minus 1 over H plus G is 0 modulo P. That is basically F times R plus G is 0 mod P, where R is some pseudo random string which is like this one minus. The reason I write it in this form is because we want to like slightly generalize this. So we want to pick instead of a pseudo random string R such that satisfies this thing, we want to pick R as a random string, a fully random string. And then let T be a pseudo random string generated by R, so F times R plus G. So and the hope is that this T looks completely independent of R to a computationally bounded. Okay, so here's how we do it. Here's how the system looks like. So T and R are the public key, and the secret key is F. So when we compute a C1, which is A times R plus B1, where A and B1 have small Hamming weight, and we compute another string P2, which is A times P plus B2, where A and B2 again have small Hamming weight. So if we ignore this additive small Hamming weight term, then basically C1 looks like A times R, and C2 looks like A times F times R, where we again ignore the small Hamming term. So basically F times C1 should be somewhat close to C2. So what we do is we compute another string C, which is C2 XORed with some error correction code of the message M. So the encryption of M is the string C1, and C2 XORed with the error correction code on the message M, so the message M that we want to encrypt. Okay, so when we try to decrypt, we compute F times C1. As I said, if we ignore the small additive additive terms of small Hamming weight, then C2 basically looks like F times C1. And in particular C2 looks like C2 prime. And so when we XOR this C2 prime and C, we should get back E of M, except with some small error. So there might be some bits that are flipped. And since we have this error correction code, so when we decode, we basically remove all these errors, so we get back to this. So again, what I did was I said like, okay, let's remove the small additive weight string, and so small Hamming weight additive strings, and then this should exactly match. But these might add some error. These will add some error actually. So which will cause this to have some bits flipped, but we will recover the message as long as the error correction code can tolerate some bits. So I repeat the analysis of decryption again. So C2 is A times T plus B2, which is A times FR plus A times T plus B2. I just plugged in the value of T, which is FR plus G. And C2 prime is F times C1, which is F times AR plus B1, which is AFR plus B1. So the Hamming weight of C2 XORed C2 prime, which is what we did in the previous slide, we did this. So we actually did C2 prime XORed C2 and XORed EM, right? So the Hamming weight of C2 XORed C2 prime is essentially the Hamming distance between C2 and AFR. So this is this small weight string plus the Hamming distance of C2 prime and AFR. So this is just the triangle inequality, and thus the decryption. So the encoding of M XORed with small error should give us back the message. So the error. Okay, so let me just go first to how this error should look like. So here's the lemma that we show, which is that if u is a random n-bit string and x is some n-bit string of small Hamming weight, then the probability that the Hamming distance of u and u plus x, so when we add a small Hamming weight string, the Hamming distance should not be more than 2 times h. I mean, like should not be significantly more than 2 times, except with some small problem. So, why is that? So that's why I mean, this proof of this is slightly involved, but let me not get into the proof. I'll just kind of try to explain why this is the case. So think of, let's say this is the string u, and this is the small Hamming weight string x. So notice that whenever we add a 1, again we are doing the same kind of operation that we did earlier, which is that, so let's say we have a 1 here, so since this was a 0, so we just have a 1, so single. So this changes only one position, so only one Hamming. So Hamming weight shifts by 1. When we add a 1 here, since this was a 1, this changes to 1, 0. When we add a 1 here, since these two were 1 and the next is 0, so this 0, 1, 1 changes to 1, 0, 0. And when we add a 1 here, again this 1 changes to, sorry, so there was a 0 here, so 0 plus 1 is 1. So notice that basically the number of positions that you are changing is essentially the number of the continuous number of ones that you see when you look at that position and go left. So the number of ones that you see plus 1. These are the number of positions that you are seeing. And the expected number of, I mean, like this is a simple calculation if you have a random string. So let me repeat that. I said that u is a random string. When you have a random string, the expected number of ones that you see is 1. I mean, this is an easy calculation. And so the amount of Hamming, so the number of bits that it would contribute to the Hamming distance would be basically about 2. So if you do it over enough number of steps, then by Chernoff kind of bound, it's like exactly Chernoff does not work because everything is not fully independent and so on. But like you can do something similar to Chernoff and get that the Hamming distance is bounded by 2 times h plus something small with high probability. So what this means is that the total number of errors in the cryptosystem that I just showed you is roughly like 2 times h squared plus h. So this 2 times h squared plus h is simply coming from, so there is the, notice that there is ag plus b2, so there is an h squared plus h contribution here, so this h squared comes from these and h from this, and there is an h squared contribution here, so it's h squared plus h plus h, then h squared plus h, and the factor 2 comes from the lemma that I just mentioned. So the total number of errors that we expect is 2 times 2h squared plus h. So as long as we have an error correction code that can correct e errors out of n, where e is this number 4h squared plus 2h, then we are fine. So I mean, we have error correction codes that can correct a constant fraction of the number of errors. So as long as n is a constant multiple of h squared, when the constant is large enough, we have candidates for error correction codes that would work. In particular, we can use Leaf-Muller codes by picking n to be something like 30, 40 h squared. So the number e is clearly an overestimate of the number of errors that we would see in practice. So notice that this bound of the product of Hamming weight is the product of the the Hamming weight of the product is upper bound of the product of the Hamming weight is clearly an overcounting, because we would be typically getting much less, as I mentioned when I described that lemma. And additionally, the previous lemma, this one, is also overcounting in this sense that right now in this example, you see that all these kind of operations, that this addition operations, are basically disjoint. But when you have a larger Hamming weight string, this would typically not be the case. So there would be a clear overlap, and the overlap would basically bring the Hamming distance down, not go up. In particular, you cannot hope to have the Hamming distance more than n over 2 or something. That's the kind of thing. So So what I'm trying to say is that this number, of course, we can use this kind of error correction codes and this all works. But this is a bit of an overestimate, and it's not so useful in practice because n becomes something like 40 h squared, which is pretty large. I mean, if you want to make this work provably. So what we see is that the number E is clearly an overestimate of the number of errors that we see in practice. Also, we expect the errors to be distributed fairly randomly. I mean, we don't expect that there are a few bits that have an error and then everything else is completely without error. So if the errors are distributed fairly randomly, then we don't necessarily need these worst case kind of codes. I mean, these codes correct errors from anywhere. But we should be happy with codes that correct error, like even if the error is distributed randomly. Let's say each bit is flipped with some probability. So, I mean, we are not able to analyze exactly the error pattern, but we do see that it is a huge overestimate what we are doing here. And so, what we actually recommend as the parameters in practice is that n is, notice that this n is a Mersenne prime, so it's a Mersenne prime. So 2 to the 7, 2 to this n minus 1 is a Mersenne prime. And this n is not like 40 h squared as I mentioned, so we pick h to be 256, and n is some constant times h squared, but this constant is not too large. And what we can do is we can just use repetition codes. So we can basically, for encrypting each bit, so we are encoding, let's say 256 bits, so that the message is 256 bits long, and we are encoding each bit with a 2048 bit repetition. So we're basically encoding a 0 as 2048 zeros and so on. And then we simply do a majority decoding, and as long as the error is distributed fairly randomly, this should still work. And we actually show experimentally that it does. So here's the experiment that we did. So if we do it with these parameters, then the error, basically the number of bits that go wrong, is follow a fairly Gaussian curve. Basically the number of, so it's like extremely low probability that it would go beyond the half mark. So the majority decoding should give us the correct answer. It's very, very high. I mean, of course, it would be very nice to prove it, but we tried quite a bit. I mean, we could not kind of analyze this with the repetition decoding. We can, of course, do it, and I mentioned the analysis if we use, let's say, bullet codes or something, but with repetition we don't. So this would be a good question to understand. So, in particular, the problem that this cryptosystem is based on is that a string R1, R2, and when we take the linear combination of the low hanging bit, so A times R1 plus B1, and the same A times R2 plus B2, these four strings should look like four independent and uniform to any computationally bounded. This is the hope on which the cryptosystem is based, and just a small remark, this assumption might look, I mean, somewhat similar to the learning with errors assumption. Of course, like there is, in the learning with errors you have polynomially many samples, but so the fact that this is A times R1 plus B1 and A times R2 plus B2, this looks quite similar to that, but we don't have any reduction either way. So we don't have any reduction in learning with errors. So in that sense, I said that it is not really lattice because we don't really know any errors. The standard lattice is. So let me show how to make it CCA secure and in the random order model. So for a CCA secure key encapsulation mechanism, what we try to do is we have, so there's Alice and Bob. So Bob has Alice's public key, and Bob has an encapsulation algorithm that should output a shared secret key and a ciphertext that is sent to Alice, and Alice, using her secret key, and runs the decapsulation algorithm to obtain this shared secret. That should basically match this. So that's the idea. And even if the adversary is allowed a chosen ciphertext attack should not be able to. So the idea that we use basically is that whenever the adversary tries to send an invalid ciphertext to the decapsulation algorithm, I mean, like basically tries to obtain the decapsulation of an invalid ciphertext, we always output a special symbol bottom, which basically we flag an error, except with very, very small. So with almost probability 1, we give an error whenever an invalid ciphertext. So the way we do it is we take a random seed S, and then we initialize a pseudo-random generator from the seed S. And so what Bob does is produces a random shared secret, and then runs the encryption procedure that I just mentioned for this string S, and basically, and where the A, B1, B2, these key strings are obtained from the pseudo-random generator. So notice that there is no randomness coming from anywhere else except from the seed S. So everything is deterministic given the seed S. And then the output of Bob is the ciphertext that is sent to Alice is C1, and the shared secret is Z hash. This pseudo-random shared secret is Z. That is produced by Bob. Then the decryption procedure, we run the basic decryption procedure on this ciphertext C1, and when we obtain the string S, so when Alice obtains the string S, what Alice does is Alice runs the whole encryption procedure with the string S. So since the only randomness was coming from the string S, you can still do this complete procedure, and you basically again obtain C1Z and compares whether these match or not. If they do, then we get the shared secret, which is Z, and if they don't, then we obtain totally basically so Alice flagged it, right? So the trivial attack on this scheme that I mentioned, either for the 1-bit case or for the multi-bit case, is runs in time n choose h. You simply can basically just choose, you can generate the secret key in that time. Like basically choose one of them, one of f or g in time n choose h, and you obtain the other. So you can try out different possible f or g. And the best known attack, this was basically proposed soon after we published the system, runs in time through to the 2H. This is not by us. We don't want to use these. So this is the best known attack at this point. Classically, is through the 2H. And if you can run LLL on a quantum computer, then this attack runs in time through the edge. For a quantum. So that's the best known attack. It would be great to kind of come up with faster or better attacks. So there is plenty of future work that is possible around this. The most important, I would say, is trying to come up with better attacks. Like, it's fairly new, so it requires work on it, study it, like before we can kind of trust on this system to come up with, try to come up with new attacks. And there are various ways to consider to try to improve the efficiency in particular. Instead of like talking about integers modulo p, we can do the same operation in every rings. We can have different coordinates, improve the efficiency without hopefully compromising the security. We can make it more efficient while still having the same kind of security. Then this would be and kind of create a service. Thank you.
So thank you very much for your talk. There's room for questions. while the people are getting ready for questions, let me ask a quick one. So in the last slide where we're going through text, I mean from the data flow, it looks a lot like ntrue, but with numbers instead of with integers. Has anybody looked into low memory attacks? Because my understanding is that the attacks here are like huge memory.
Not yet. By low memory, you mean like
Collision search, but not with base. I mean, like when you're doing the searches, you do like we have an all-shot attack, and then instead of having the huge memory, you try to reduce it.
no, not
Okay. I mean, it will make the attack slower, but more realistic, so
yes.
it's not a danger.
Right now, people have tried to kind of calculate what is the, I mean, in terms of getting the right number, what is the correct runtime for the attack, but like, of course, if you want to make it practical, these kind of stuff.
Anybody else? Yes.
You may have received this question behind, what is the advantage or disadvantage of this cryptosystem compared to Redis cryptography in terms of time and space complexity?
In terms of time and space complexity, I think it's not advantageous, or it does not. It's kind of incomparable in the sense that we don't really know the security of any of the crypto systems, and particularly just try to guess it. Right? I mean, like that's true for lattices, that's true for this one, in some sense. But apart from that, I mean, like the main advantage is the simplicity, but it's not so much the security and everything. I wouldn't really be able to compare that because it's very.
And the second question is that if the best known of the complexity is exponential on age, then why the recommended parameter had a much larger age?
No, age was 256.
So 256. Okay.
Age was 256. N was much larger because n has to be h squared times.
So basically we first decide age based on this.
Yes,
effect.
exactly. So the h was chosen based on the best attacks.
Okay, thank you.
Any more questions? I realized there was some ECC in there, just didn't need a little bit of cryptography, but error correcting codes. That didn't wake up anybody. All right. I woke up two people.
So, Mersenne like,
Yes.
so, there. So, is there some modification or some way to modify to have a more wide range or sort of large range of parameter choice, flexibility of this
So,
scheme?
Um,
Some other
I'm
kind
sure
of prime can be applied.
other kind of prime, I'm not so sure. The Mersenne primes are like very nice in this respect because you know these like this thing that I explained.
Yes, but very limited. And
Sorry?
so there are no flexibility to choose a security level.
Also, okay. So what we can do is probably work with Mersenne numbers in general, like the numbers of the form 2 to the n minus 1, where n is a prime, but it's the number is itself not a prime. This should be okay. We just did not mention that because like there might be some unforeseen kind of possible if the number is not a prime. So what I'm saying is that p might, if p is not a prime, this should still be fine, but n should be a prime. I mean, otherwise there would be attacks that's possible. So that pretty much answers the second of flexibility, right? I mean, if you can use any prime number n for your choice of side, so you have to analyze that.
Last question there.
So since we are at ECC, so probably it is a good time to wonder if we can have some crypto system based on elliptic curves and try to reduce the size of the Mersenne prime by half and replace the affine transformation by some point addition on the elliptic curve. Do you consider it?
We did not consider it. I'm not
converted electric photography at all. So maybe people here can help us help with this.
That sounds like a great discussion over the coffee break, which brings us to the next agenda item, namely the coffee break, which we will shift slightly because we've been running late, so we will start again at 45, not at 40, but 45. Please be here on time. A request for the next speakers, can you please check that your laptop setup works, and